going to talk here about section 2.1 on our book, Velocity and Speed. So we have here a little table of values, and suppose we throw or kick or shoot or launch some object into the air, and we measure its height at different time intervals. So you can see in the table that we're measuring time in seconds and height in feet. So first, I want to direct your attention to those yellow questions. So in general, in this class and on an AP exam, when we are given a numerical representation of a function, what kind of things can you assume and what is not safe to assume? So the first is, how about the values between points? So we have to be very careful unless more information is given in the body of the question. So sometimes we may be told things like is continuous or differentiable, whatever that means, or that it has, a maximum height at, say, t equals 3 seconds, or, different things like that. But unless that information is specifically given in the question, it is not okay to assume that. So, for example, we don't know really what's happening, say, between t equals 5 and t equals 6. So it looks like, according to the table, that, if you were graphing this and you had height and you had time, that at time 5 it was up here at 100, I think that's 106 is supposed to be, and then at time 6 it's down to 30. And we would think that that's going to do this, but we can't really assume that it doesn't do something really crazy in between there. So unless we have specific information, we can't really assume that. Now in this case, if we're throwing an object in the air, we know a little bit more about how it's going to behave because, if we're here on Earth and we have gravity, then it's a little more predictable. But in general, we can't assume anything about those values in between. We certainly cannot assume anything about maximum and minimum values. So it looks on the table like 162 is the maximum height, but we don't know that this thing really, that if we're graphing this, that it has a maximum height at 3 and then it comes down. It could be that this thing actually reached a maximum height in between 2 and 3 seconds and then was on its way down at when it was at 162 feet, or it might have gotten even higher after 3 seconds and then was on its way down when it was at t equals 4 seconds. So we certainly can't assume anything about maximum and minimum values just looking at the table. Also on continuity, and later when we talk about differentiability, these are things that cannot be assumed unless they are given to us in the body of the question. Okay, so now let's talk about the speed and velocity thing. Suppose we wanted to know the speed at t equals 3 seconds. Well, we can't really tell what that is here, but what we can do is look at an average. So we can look at an average speed, or we're going to actually consider it here, first an average velocity, and then we'll talk about how speed and velocity are related. So for an average velocity here, we can't get the instantaneous value at 3, so we could, using this pre-calculus notion, we talked about this a lot in AP Prep, that an average rate of change is really just like our old Algebra 2 idea, the slope of a line, that is in functional notation, that's f of b minus f of a over b minus a, or in our case, since we're interested in the velocity or speed rather at 3, we could use a couple of points on either side, or we could look at the one immediately to the left and right of 3. That is, we could look at, say, h of 3 minus h, that's supposed to be an h, I'm locked into f notation, h of 3 minus h of 2 over 3 minus 2. And so that would be 162 minus 142 over 1. So that would estimate then, or approximate, that our velocity or speed would be 20, and that's going to be in feet per second would be the units on that. So y units over x units, or dependent variable units over independent variable unit. Now, it would also be a reasonable thing to do, say, h of 4 minus h of 3 over 4 minus 3. And so if we chose that, we would get 150 minus 162 over that 1, and that would then be a negative 12 feet per second. So what we're seeing here is it's going to depend on where that maximum was. Here we're estimating it perhaps on the way up, and here we're estimating it as that object is on the way down. Now, the difference between speed and velocity is velocity, as you can see here, these are both velocities, average velocities. They can be positive or negative, and so that's communicating a direction. A positive, in this case, since our object is either moving up or down, it's going to be moving up, and here we're saying the object is moving down. Speed, let me try to spell speed correctly. So speed is going to be the absolute value of velocity. So speed is going to always be positive or 0, but never negative. So a speed going up is going to be the same as the speed going down. Now, we looked here, we are trying to approximate the velocity at 3, what we'll call the instantaneous velocity or speed. And we tried estimating it using values to the left and to the right. It would also be reasonable to try to use those two values, one right, one left. So it would be reasonable to try to do h of 4 minus h of 2 all over 4 minus 2. And so that would be then the 150 minus the 142 all over 2. And that would be 8 over 2 would be a 4 feet per second. So this comes up sometimes. It may come up in your homework. It comes up pretty regularly also on AP questions, actually. And if they don't direct you which one to use, they would accept any of those three answers as a reasonable approximation. Now, what we want is to get a better approximation. So to get a better estimate, to get a better estimate, what we need a smaller delta t. We need, I'll just say a smaller delta t, which we will sometimes refer to as h. So in the case of our table, we don't really have an option of trying to, find out, we don't know what the value of the height was at 3.5 seconds or at 2.5 seconds or perhaps at 3.1 seconds and 2.9 seconds, which we could use then to get a better approximation, a better estimate. So to get a better estimate, we either need more data points or we might need an equation. So we're going to say that, I'll give you that equation. So the equation that generated those tables of values was 6 plus 100t minus 16t squared. So now if we want to get a better estimate, and you'll be asked to do this on your homework, we could, for example, try to do, I'm going to say the height evaluated at maybe 3.01 minus the height evaluated at 3 all over 3.01 minus 3. Can you see what I'm doing is f of b minus f of a over b minus a? If you do that and put it on your calculator, I believe you're going to get 3.84. So that would be a better estimate, certainly, than the ones that we got up there in the blue. Now, we could improve that, we would think, even more if we chose an even smaller difference there between the place where we want to estimate the velocity at time 3, and the distance away from that we're going to use. So if we did something like h of 3.001 minus h of 3 over 3.001 minus 3, then if you put that on your calculator, I believe you'll get 3.984. And so we could keep doing this, and each time we choose a smaller delta t, or smaller value of h, then we're going to get a better approximation. So it looks like, anyway, that this is trending towards 4.0, and that would be in feet per second. Okay, so that's our estimate there. So to kind of summarize, a velocity can be positive, negative, or zero. A speed is the absolute value of velocity, so it will always be greater than or equal to 0. So speed can never be negative. Okay, I'm going to get a new panel up here. So the average velocity, which is the average rate of change of the position of that object, so this is a topic we talked about a great deal in AP Prep, the average rate of change. The, I guess, new twist or different twist at this point is that we're talking about a specific function, not just a function in general. So if we're talking about a position function, then the average rate of change of position we call the average velocity, and that's going to be given by, this is our old familiar slope formula. So it's y2 minus y1 over x2 minus x1, only it's written in function notation. Now, if we want to look at the instantaneous velocity, so we are interested in finding not the average velocity, but the instantaneous velocity at t equals a, then we're going to first think about changing our notation a little bit. So this hopefully will remind you of stuff that we did a lot in our AP Prep days. So if this is our position function, so I'm going to say this is y equal, or I'll say s of t. I'll just say y equals s of t. So there's our position function, and we have our point A that we would like to know the instantaneous velocity, and this is our point B. What we have done in our average velocity in our AP Prep or pre-calculus days is we have found the slope of that line joining those 2 points, which is known as the average rate of change. What we would really like is to know what it looks like geometrically is going to be a slope of a tangent line right at that point where t equals a. So we're going to change up our notation a little bit here, and instead of just calling this a and b, we're going to say this difference between a and b we're going to call h. So that's going to make the b we could also now refer to as a plus h. And so then our instantaneous velocity at, or first our average velocity, I'll say, at the same thing we've done over here is going to be s of, I'm using s instead of f, and instead of b, I'm going to say a plus h, and then minus, instead of f of a, I'll say s of a, and in the denominator, we're going to have our b, which is a plus h minus the a. So that is going to, we'll let those a's cancel. So it's going to look like s of a plus h minus s of a all over h. This may be bringing back fond memories of last year. Now that's our average rate of change, our average velocity. To make it instantaneous, we're going to put in here the limit as h goes to 0. And that becomes our instantaneous velocity. So that's a big part of where we're headed here. Let's take a look at a graph here and just talk a little bit about what we mean about where is an average velocity going to be positive, where is it going to be negative, and where is it going to be 0. So let me choose a different color there. So I'll pick green. So our curve is going to do something like this. And so here is our function, and we're going to say that we have time coming along the horizontal axis and the distance d going along the vertical axis, and I'm going to call this point right here B. So the question I want you to think about, questions, is where is the average velocity positive? And where is the average velocity going to be equal to 0? And where is the average velocity going to be negative? So I'm going to introduce some colors here. So we can see that the average velocity, so if you're looking at where the slope between points on the curve is positive, it's going to be anywhere that this curve is rising from left to right. So it's going to be all along here. And then we'll jump down over here, and everywhere along here, we're going to have slopes of lines joining 2 points on the curve will be positive, which is what's going to tell us the average rate of change is positive. Now, interestingly enough, it will be 0 right at the very tops. Let me change that from green to red because I have my curve is green. So that's going to be here, and also here are going to be 2 places. Those are the x values I'm putting here, where the average velocity would be 0, and then where it's going to be negative is going to be along this part of the curve, where when we pick any 2 points on the curve, the slope of the line joining those 2 points is going to be negative. Okay, so I'm going to go to a new panel here. I put a couple examples here, and these are kind of problems like you will see on your homework. And so it's going to ask you to estimate the limit as h goes to 0 of 2 to the h minus 1 over h. So they don't really give you a whole lot of direction, but since we're approaching 0, what we're looking for here is just to approximate that limit by using an average rate of change with h really close to that 0. So what we can do on our calculator is maybe choose h to be 0.001. So that's an h value that's going to be really close to 0. So if on our calculator we plug in 2 to the 0.001 minus 1 all over 0.001, then I believe we're going to get 1.611. So that would be a way of estimating our limit there. And we'll learn other ways of doing this that'll be a little more precise. But at this point in time, what the authors of our book are trying to get you to do is think about a limit as h goes to 0 means we're plugging this in, we're plugging values of h that are getting very close to 0. Now you might, I'm going to challenge you a little bit here, and if you can think kind of in terms of what we were headed towards there, if we were taking the limit as h goes to 0, and you may remember from our, I'm going to call this, say, a plus h minus f of a all over h. This is kind of where we're heading here, very much where we're headed here. And so what's happening in this case is, and I don't know if you can recognize it, but the underlying function that's not really being stated here is f of x equals 2 to the x. And that's not important just yet, but we'll get to that down the road. So on the next one, I'm going to do a similar idea. This is a little bit of a twist on what we did before. So this is actually a version of our our favorite limit problem, where we're doing f of a plus h minus f of a minus h all over 2h. We'll talk more about this down the road. But at this point in time, if we choose h to be 0.001, that's going to be really close to 0. And then we can just grab our, actually I'm going to ask you to, hold on, I'm going to ask you on this one, I'm going to take that back. So instead, I want you to do this one using algebra. So we're going to estimate this, estimate using algebra. This is really where we're headed soon. So we're going to actually square out that 5 plus h. So that's going to be the first one squared twice the product plus the second one squared. We're going to subtract from that the first one squared twice the, oops, that's a 10, twice 5 times h is 5h times 2 is 10h, plus the second term squared. So that is, so this is the 5 plus h squared, and this is the 5 minus h squared, all over 2h, and we're going to take this limit as h goes to 0. So we are going to distribute that negative sign, so that's going to become the limit as h goes to 0 of 25 plus 10h plus h squared. That'll be a minus 25 plus 10h minus h squared all over 2h. Now you may remember when we did this before, anything without an h in it is going to find something to cancel. And in this case, even the h squareds are going to cancel. So that is going to get us to the limit as h goes to 0 of 10h plus 10h is 20h all over h. We can cancel those h's, so now it doesn't really matter what h is doing. What we're going to get is 20. And so that is that limit. That is going to be an instantaneous rate of change of something, because we didn't really see what it is. But underlying there, kind of lurking in the shadows, is there's a function there that is actually our square function. But we don't have to know that and recognize it just yet. All right, very good.